All right. Hello, everybody. Welcome to chapter 20 of the Effect Book Club. It says chapter 1 on the screen, but that's because I just have open the HTML file for the single chapter. So it's actually chapter 20. Today we're going to be talking about regression discontinuity. And I've just turned on Do Not Disturb because I don't know if you could see my notifications before, but I had emails popping up. Um, all right, so our objectives for this chapter, which will take us 2 weeks, and this is the first of those weeks, is to understand what regression discontinuity, also known as RD, is. Uh, we'll learn how to perform basic RD analyses and understand some variations on regression discontinuity that may be used for more complex analyses. So, regression discontinuity, or RD, is a technique that we can use when there is a treatment that we're interested in looking at that is assigned at a cutoff. So on one side of this cutoff value, there is no treatment, but as soon as you cross that threshold, there actually is. So we'll define some terminology here. The first is the running variable, also known as the forcing variable. And this is whatever variable determines whether you are treated or not. So an example that the author included in the chapter was blood pressure. So below a certain threshold, you will not receive blood pressure medication because your blood pressure is in a healthy range, but above a certain value, you would start to be treated with a medication to help with hypertension. So a cutoff, therefore, is that threshold value. So the value of the running variable that determines whether you get treatment or not. And of course, with blood pressure, I cannot remember what the value is, especially because it de depends on the like systolic versus diastolic blood pressure. And I literally did my blood pressure yesterday and still cannot remember what the cutoffs are. Um, then our last little bit of terminology is bandwidth, and this is how much area around that cutoff value you are considering in your analysis of regression discontinuity. As we'll see later, the bandwidth is technically optional. You don't have to include a bandwidth, although in some data sets it's generally a good idea. So the idea behind regression discontinuity and why it should work for causal inferences is that we're basically trying to carefully select the variation in our data that lets us ignore backdoors without having to control for them. Or more precisely, we are isolating a front door path between our treatment and outcome. We are doing this by assuming that cases that are just barely on either side of the cutoff are only different or like vastly different because of the treatment, and that they're otherwise randomly assigned, and there's going to be no major differences other than in whether they receive the treatment or not, as long as they're really close to that cutoff value. So if you had a cutoff value of, um, you know, somebody receiving like a supplemental income grant at $40,000 a year, you would assume that somebody making $39,000 a year and somebody making $41,000 a year are probably vastly similar. The only difference between them is whether or not they're getting that sort of extra little bit of income. Before we perform regression discontinuity, we have to make two choices. The first is what method we're going to use for predicting the outcome on each side of the cutoff. And then the second is what value or what level of bandwidth we are going to be using. And actually, that bandwidth argument is optional depending on the quality and characteristics of your data set. Um, and as we'll see, you can also um, you still have to make these choices, but you don't necessarily have to just choose one method and one bandwidth in your analysis. You can run a whole bunch of them and start to compare. So it's decisions, but they're not life or death decisions, that's for sure. And then very, very, very generally, what happens with regression discontinuity once you've made those choices is you go through a few different steps. So up in the top left here, we have our raw data. So we can see here is just a scatter plot with our running variable on the x-axis and our outcome variable on the y-axis. We have a vertical dashed line in the center there, and that's representing our cutoff value. And we can see that, we've got a relationship going here, and it looks like there's probably some differences in the relationship on either side of the cutoff. We then need to predict the values near the cutoff using whatever model we've decided to use to predict the values on either side. Here it's a Loess regression, and you can see here that we've got sort of a regression that goes on the lower side of the outcome variable on the left and on the higher side of the outcome variable on the right. And at our cutoff, there does appear to be a jump in our values of the outcome. The third step is to pick a bandwidth. So this is, again, the sort of amount of data on either side of the cutoff that we're going to be looking at. And here, I mean, we don't know what the bandwidth level is here because it's not labeled, but we've basically subsetted our data to be very narrowly around that cutoff so that we're hopefully getting rid of any other variables that might be influencing the data further away from those sort of middle values. And then essentially what we do is we estimate that jump. So there's a vertical line here. And essentially what we're doing is we're just calculating the difference in the mean values between the mean values of our data on the left side of the running variable and on the right side of the running variable, and that's going to be our estimated discontinuity. So that's like the very general sense. Of course, there are a whole bunch of different ways that you can uh, elaborate on this, a whole bunch of different stuff. One of the ways that things can be different is with what we call fuzzy regression discontinuity. So in many RD applications, being on one side of the cutoff doesn't necessarily mean that you will guarantee to be treated or guarantee to not be treated. Instead, it only changes the probability of treatment. So what we just looked at is what we would call a sharp design, where on the left side of the cutoff, or it could be the right side of the cutoff, but on one side of the cutoff, you have a proportion treated of 0, and on the other side of the cutoff, you have a proportion treated of 100 in many real world cases. And the author used the example of retirement age and retirement. Uh, Instead, your proportion would go up slightly on one side of the running variable, and then it would have a major jump to be much higher at the cutoff, but it wouldn't go all the way up to 100, and there would still be an increase in the proportion treated over time or over values of your running variable. Um, and despite the fact that I worked on these for like 45 minutes to an hour, that is where my slides end. And it feels like that was a lot of work for like 10 minutes. All right, so I've got
Mhm.
here, now you should be able to see the book, right?
Yep, we
Okay,
see it.
perfect. All right, so then we get into how regression discontinuity is performed. And we start with just doing RD with ordinary least squares. Um, So we're just going to start with a very simple regression. I mean, this is an equation that I think we could all recognize pretty easily at this point. Just very simple OLS. So generally, when we're doing RD, we estimate the model using heteroscedasticity, robust standard errors, because we might expect that the discontinuity and the general shape of the line we're fitting will have some heteroscedasticity in most cases. Of course, there's arguments about how you want to do heteroscedasticity, robust standard errors. You can use sort of, I guess, a few different a few different methods of doing it. And the author helpfully points out that some one of the common ways to do it used to be using standard errors that are clustered on the running variable, and that's no longer thought to be helpful. So, as always happens in any sort of scientific pursuit, you get new data, and then you're like, oh no, everything we've done in the past might be wrong.
Yeah. Yeah, we've seen that a couple times in this book
Yeah.
already.
So, one thing that the author expressly points out here is that there are no control variables in this equation 20.1 up here. Um, Most of the time, this is done just to focus our attention, but it's actually very intentional with regression discontinuity. Because as we talked about earlier, we're trying to carefully select our data so that you have nearly random assignment on either side of the cutoff. And because of that, you shouldn't need control variables because the design of regression discontinuity should be closing those backdoors. Um, that's not to say that you can't add control variables, and there are cases where that has been done. It's just that, in the optimal perfect RD design, you wouldn't need to. Do, do, do. So, I think I was not going to talk about this a little bit. No, maybe I was. Okay, so basically, once we have started doing our analysis, we end up with two straight lines. So this is once we apply this equation up here on either side of our data, we get two straight lines. One has the intercept beta 0 and the slope beta 1. This is on the untreated side of the cutoff. And another has the intercept of beta 0 plus beta 2 and the slope of beta 1 plus beta 3. So we can apply this regression to simulated data, which results in figure 20.5 here. And since we've centered our running variable to be 0 at the cutoff, so here this sort of cutoff value in the middle there is 0, anything to the left is going to be negative, anything to the right is going to be positive. The intercept of each of these regression lines on the left and right is our prediction at the cutoff. And that is really helpful because basically all we need to do is subtract our intercepts in order to get our estimate of the regression discontinuity effect. And that's super fun. So an obvious benefit of this sort of really simple OLS method is that it's super easy to do, like we just discussed it in 5 minutes. Um, but of course, easy is not necessarily a good reason um, to pick a method. And the pros and cons are kind of all intertwined together. So we're using a fitted shape to predict the outcome at the cutoff. That's helpful. Um, But it also means that our decision of bandwidth can really impact what shape we're getting, as well as our decision of model. So we really need to be applying the right fitted shape. We can see here, and this is the same as figure 20.5 above. This is figure 20.6. It's the same as 20.5, but we've highlighted some areas around our cutoff that look to be like they're maybe not fitting the model that we actually fit. So the model or the issue is really obvious because fitted shapes tend to be the most wrong at the edges of the available data. It's really obvious on the left side of this cutoff here. You can see we've got essentially a U shape in the data. And since we fitted it with a linear model, we're getting just a straight line that's not super right in the middle, but seems to be closer to the data points. And then at the edge, right where we're at the cutoff, our data is like going up into space, and our linear model is not capturing that at all. So obviously we can just start to fix this by using a more flexible shape. And this would be having a flexible function for running minus cutoff. So for our sort of running variable there, or centered running variable, I should say.
So just to be clear, right, like fitting regressions to the edges is always a problem, regardless of whether or not we're doing RD.
Yes.
But here, I'm assuming we're considering the cutoff itself to be an edge.
Yeah.
Is that right?
Yeah. So essentially what you're doing is because you're basically fitting two different models, one on one side of the cutoff and one
Hmm.
on the other side of the cutoff. Um, and then comparing them. But as you as you said, that cutoff is by definition an edge. It is going to be either the high edge of one of a model or the low edge of another model. So if your regression is poorly fit and the edges tend to be most wrong, then your discontinuity is going to be extra wrong.
Hmm.
So that sort of makes sense. So yeah, this just goes to show that when we were talking earlier, like choosing a model is sort of easy, but also it's sort of hard. Um, so we can pick more flexible models. We can see here an example where we're testing a whole bunch of different polynomials as well as a linear model, but with a bandwidth, instead of fitting the entire left and right side of the cutoffs like we did earlier. Um, it's always tempting to just be like, make it more flexible. But as you can see, the order two polynomial here, I mean, it looks like it fits the data pretty well. The order six fits the data more closely, but we do start to get a little bit of wiggle. And then the order 25 polynomial is just sort of not super useful because it's just all over the place. So the authors suggest here that because things start to get a little bit wacky with higher and higher polynomials, the author suggests that it's not a great idea to go above the second order term when performing RD with ordinary least squares. And instead says that if there's a really complex shape that needs to be fit, try limiting the range of the data with a bandwidth to use as simple a shape as possible.
Yeah, and there's a reference to what an article by Gelman, who's kind of all over the place with causal inference and Bayesian stats.
Yeah, I also really enjoy the title of that paper. It's like very clear and to the point. It's just
Yeah.
like, don't do
Yes.
it. So we can think of this approach where, we zoom in to a bandwidth and use a model that's as simple as possible as what we call a zoom in and go simple approach. We can think of that as a local regression. So, with a local regression being one that estimates the relationship between a predictor and an outcome as normal, but allows that relationship to vary across the range of X. Most people are going to implement regression discontinuity with some sort of local regression, especially if they have a large sample. And essentially, what local regression is doing is for each value of x, so maybe we have x equals 5, it gets its estimate of y by running its own little x equals 5 regression. So at each value, it's running its own little regression. It will therefore be weighting observations much more heavily the closer they are to whatever value is being done in that particular regression. When we're doing this, that weighting, so weighting x equals 5 really, really, really high is called a kernel. Sometimes the kernel is a cutoff, so the weight is 1 if you're close and 0 if you're far away. But other times is more gradual, so it sort of ranges from 1 to 0 depending on how close to the kernel value you actually are. Very commonly, what's used in RD is the triangular kernel, which is the one that's figured right here. So you've got your central value of x, and that will have a weight of 1. And then you have the sort of lower and upper bandwidth, and the value of your weight sort of decreases linearly from the central value to the lower bandwidth and in yeah and to the upper bandwidth. So it's highest at the central value and moves down to 0 as you approach the bandwidth cutoff. Um, nope.
And there's tons of kernels out there, it's
Oh
just
yeah.
interesting how I'm sure there was some influential paper that used triangular, and so then everybody else decided, hey, I'm going to use this too.
Yeah, I also wonder if it's maybe r relatively computationally easy compared to other options. Um,
Or it
but
might not matter.
or it might not matter, yeah. Also, my computer has, oh, no, there we go. Sorry, my computer like froze Firefox and I ended up scrolling forever. Um, yeah, because I guess like if you, I mean, I guess like a kernel, a, a ver a like a cutoff kernel would be the least well, I don't even know if it would matter
Yeah.
computationally. Anyways,
It was just
this one
interesting. They
is
noted this is what people are using, and I just kind of thought about like why that would be.
yeah.
Um,
Especially because like I'm so not used to seeing like something like this where it is literally a triangle. I'm like
yeah,
didn't want to use like a normal distribution or something like
right. The
that.
Gaussian kernel I think is really common too out there, right?
Yeah.
And other applications. So it's like why go with this one?
Um yeah, that's an interesting point. Um so the author does note that local regression does take a lot of computing firepower, but it's conceptually very simple. You just roll along the x-axis and make a whole bunch of new regressions as you go. Um, I can't say I've actually performed local regression, so I don't know how like computationally intensive it is with
Honestly,
today's machines. Like,
yeah. Compared to regression, okay, but for most like real life data sets that aren't like these, billions of data points,
yeah,
this stuff runs pretty quickly. In fact, I typically don't use local regression for modeling, but doing EDA with graphs, right? Like that's kind of built into like ggplot. When
yeah,
you're doing what is it, geom smooth.
Mm-hmm.
Like the
Yeah.
default for doing like to understand the trend of your data, it's either a GAM or a Loess curve. Um, so I use those
Yeah.
all the time, and they're real quick.
Yeah, I've never tried using them with larger data sets, though. I guess that's now I'm kind of tempted to, just to see. But also, like, I have a better computer now than like the last time I was running some of these data sets. So I'm sure those, like, the analyses that used to take like 20 minutes would probably go faster today. So I don't know. Um, so if you're using these kernels, well, I guess if you're doing local regression and therefore using a kernel, the question then becomes what regression should be run at each point. Um, you might take the average, in which case you end up with a kernel regression. Um, Kernel regression can give us issues in the case of regression discontinuity, especially if there's a trend that's like leading up directly to the cutoff, because as you can see here, if we're doing kernel regression with that same data set, where we've got the sort of the U-shaped curve on the left-hand side of the cutoff, we're just getting a mean value that is not representative of that trend at all. And we would therefore probably be overestimating our discontinuity here. Um, so more commonly, we'll do local regression with the most common form being Loess, which we were just talking about with geom smooth. So instead of taking a local mean, Loess estimates a linear or second order polynomial regression at each point. And this allows the relationship between X and Y to not be totally flat as it would be with a kernel regression or taking just the mean. So, if we plan on using local regression, we don't really need to do anything special, but we're also theoretically, if we're doing um, regression discontinuity, we're not actually interested in the whole relationship. We're only interested in estimating the regression discontinuity at 2 points, just to the left of the cutoff and just to the right. So, I mean, you could just pick a bandwidth and do a linear regression. That's basically the point there is that you can do all these fancy methods, but also you don't really have to. Um, that said, there's a good chance that you might be interested in a regression discontinuity, but you also might want to know something about the overall relationship on either side of the cutoff, not just at the cutoff, in which case, like, you might as well just save yourself the time by just running the whole thing and then being able to compare. So this is very much a your mileage may vary. It depends on what your data looks like, what questions you're asking, all of that good stuff. So in terms of coding up regression discontinuity, what we've been provided with is a data set on government transfers, um, where basically this was the one in Uruguay. Yeah. Basically, there was a poverty alleviation program which cut a check to a large proportion of the population, depending on a bunch of different factors like housing, work, reported income, and schooling. They used those to get a predicted income, and that predicted income was what was used to design the cutoff and assign treatment. So about 14% of the population ended up getting payments. And what the authors were interested in knowing was whether folks supported the government more if they were receiving the um, the sort of poverty alleviation check. So the data set we have is really handy because it actually comes with the predicted income variable pre-centered. So the cutoff is already at 0. Super easy. We don't have to do that then. Then support for the government has sort of three values. If you think they're better than the previous government, you get a value of 1. If you think they're the same, you get a value of 0.5. If you think they're worse, you get a value of 0. The data already only includes individuals near the cutoff, so the centered income variable in the data only goes from negative 0.02 to positive 0.02. Um, so the first thing we want to do, and he says this is nearly compulsory, um, is to do a graphical regression discontinuity check, which is just a way to say like plot it and look at the data.
Mhm.
And just check to make sure that there actually does appear to be a discontinuity where we expect to see it. So here's our centered income and our support, and there definitely looks like there is a break at the cutoff there. So um, that's good. That seems like we're generally expecting to see RG here. So the author does note that the first step to doing RD with OLS is to center the running variable, but this is already done in our data set, so we don't have to worry about it. We can do a second order polynomial model on um, these data up here, and this will suggest that receiving payments increase support for the government by 9.3 percentage points. That's with the second order polynomial. If we do a version with the kernel weight, it shows um, sort of in contrast with that, it shows a statistically insignificant effect of 3.3 percentage points. Um, Here, the kernel weight might not be the sort of best approach because our data is already quite limited. We already have a fairly narrow bandwidth, and therefore, sort of restricting it more and sort of applying all these extra methods might not be necessary. Um, I am not familiar enough with any of this to comment on whether that is appropriate, and I will I will just trust the author's judgment here.
Yeah, it just interesting, right? How that your uh, design, the model that you're using gives you kind of radically different results here.
Yeah, I was surprised at how big the difference is. I don't know I guess the political situation in Uruguay, like, like how many parties they have, all of that stuff. But like 9.3 point difference in support is quite big.
Yeah, I would agree.
Um,
But we're also
and
only
yeah, like,
talking about this local effect, right? Because we're only
yeah,
talking about everything that's
That's true.
right at the border. So if you're very poor, basically, or no, you're just not poor enough to get the check, but you're still not
Right.
doing so great, to you're just poor enough to actually get
Yeah.
the money. So I'm guessing if you would look at the effect of giving it to the richest 10%, then it probably wouldn't cut it as much.
Yeah, you're right. This is a
yeah,
small subset of the total, so it's not like you can extrapolate that to the entire population based on
Yeah.
this.
Which is
Yeah,
really
great
sad
point.
about RDD, right? Like it's always just about those people at the bandwidth. You
yeah.
can say something about them very precisely, but like,
It kind of just gives you it like whets your appetite to do more, but you're right. Yeah, it's a small piece of the puzzle
yeah.
that what you're probably really interested in.
Yeah. Yeah, I don't know. It's very interesting. And yeah, I don't have a good sense of like I guess what sort of support for a government you would expect with like such a narrow subset of the population. Because now that you've sort of mentioned it, I'm thinking like a lot of, like a lot of folks who have lower socioeconomic status like might tend to vote, like tend to support political parties that are more likely to give these sort of, provide social security and all of that stuff anyways. So, I don't know. Interesting. So basically all of this that we just did, we did sort of by hand. We did it in a very um
Yeah, the kernel was done in a custom
yeah.
function, I think, right?
Yeah, it was a very like hands-on sort of method. But of course, there are packages that will do this for you. Um, so the author calls out the RD robust package, which is part of a whole universe of regression discontinuity packages that I now know exist. Um, there is now versions of RD robust for R, Stata, and Python. Although the author doesn't cover the Python version in the book because it was developed or released more recently, or too recently to be included in the book, I should say. So that RD robust function does some stuff that means that we have less work to do, um, arguably. So we don't have to choose a bandwidth because RD Robust will choose an optimal bandwidth selection procedure for us. It will properly implement local regression with whatever order polynomial you choose and a triangular kernel. And of course, it is called RD Robust, so it will apply heteroscedasticity robust standard errors. Um, it uses a very specific robust standard error that I'm not going to discuss. And then it also applies a bias correction. So methods for optimal bandwidth choice tend to select bandwidths that are wide, just because they're essentially trying to increase the sample size and improve precision. Um, but this can mess with our standard errors, and so there's a method that's inherent to RD Robust to correct for that and bias and improve our estimates of the standard error. I think the author does sort of get into this at some point, but something that I have definitely noticed a lot is that even though a lot of this stuff is built into RD Robust, it's still kind of important to look at the documentation and figure out how it is selecting the bandwidth, implementing local regression, all of that stuff, how it's doing it behind the hood, because I'm sure this is not the case with RD Robust, but I know of some software where the developers were um, kind of the worst, and they selected unhelpful defaults so that they could essentially judge people when they publish papers using the defaults for not actually knowing what they were doing.
That is wild.
It's just
Yeah,
mean.
it is very mean. It's very like I feel like it's very like math bro. Like I want to be, I want to show everybody how like smart I am. Um, but I think that does provide a good lesson in that like just because something is the default in a package like RD Robust doesn't necessarily mean it's going to be the optimal method for your data. So if you're planning on using RD Robust, I would still recommend like looking into the um how it's calculating everything and making sure that the defaults that it applies are either what you need or there are options for what is actually useful for your data. But yes,
Right. And so in this case, the defaults weren't great, right?
I think so, yeah, for the particular data set.
Yeah, use that head of yours.
Use that head of yours. It's always good life lesson. All right, so I'm thinking probably we'll be able to get through this little section on fuzzy regression discontinuity and then see how we are and whether we have enough time for placebo tests. So here
Sounds
we're
good.
getting into that fuzzy regression discontinuity, where we're essentially looking at the many real life scenarios where the policy isn't necessarily supposed to be assigned based off of a cutoff, but the chances of treatment jump significantly at the cutoff. Here, he's using the example of the chances that you hold a high school degree jump significantly at the summer following your 18th birthday. But, there's people who graduate high school at 17 or 19 or not in the summer or never graduate at all. Um, I graduated high school at 17, so there you go. Not because I'm super smart, just because I have a late birthday. So we've already sort of covered the basics of fuzzy regression discontinuity. Um, and we can sort of figure out how we're gonna make it work in actual practice by just modifying our causal diagram. So basically all we need to account for is that there is another way for a running variable and treatment to be related other than the cutoff. So we could go through the cutoff here on sort of the bottom left, or we can go through Z here.
We basically combine IV and RDD, right?
Yeah,
Crazy
that's exactly.
concept.
Yeah, that's exactly what we do. Which now it makes a lot of I mean, not that I was questioning it, but it makes a lot of sense that we covered IV right before RD then.
Hmm.
So the big change here is that we're not really able to simply limit the data to the area around the cutoff and then just like wash our hands of it on controlling for running variable. We would always be understating the effect if that were the case. So, as Sarah just mentioned, we do this by applying instrumental variables. We use basically the same regression discontinuity equations that we used for the sharp RDD. But these equations now become a second stage equation rather than a first stage equation. And the first stage uses above cutoff or a cutoff value as an instrument for treated. So that's where the IV comes in. So just like with sharp regression discontinuity, we can do this using our standard tools or specialized packages that are designed to do this fuzzy RDD. Um, we're basically going to do we're gonna do the by hand version first, and then we will do the sort of specialized fuzzy version. There was something that I meant to highlight in here, and then now it's gone. Oh no. Okay, so now I'm remembering what I was trying to think about. Basically, we want to make sure that our instrumental variable is not like also uh, affected by our running variable. So we've got two plots here in figure 20.13. So we definitely are seeing a sharp change in the rate of eligible veterans in this data set, which is about veterans in World War II and the Korean War and eligibility for mortgage supplements. So here, discontinuity, we see a sharp change in the rate of eligible veterans around the cutoff. And we see a discontinuity in the rate of home ownership at the same point, although the rate of home ownership discontinuity is a little bit less noticeable. And our fuzzy RDD estimate here is the jump at the cutoff in figure 20.13b, so the RD for home ownership, divided by the jump in the cutoff in the RD for eligible vet status. What we do next is we use the RD robust function in R or in Stata to do local polynomial regression, kernel weighting, all of the stuff that RD robust does. And we just need to add in the extra little bit of using their vet status as a treatment status indicator and give it to the fuzzy option in RD robust. Do, do, do. So here we've got our model with RD robust, and you can see we have fuzzy equals vet WWKO. So one of the things we want to know is if one of the models that we're using is making assumptions that are less likely to be accurate. Anytime you do a research design, you're going to have to defend these. So often, what folks will do these days is they will see how sensitive their estimate is to different bandwidths by running the model multiple times and reporting how the effect changes, therefore, sort of providing you with all of the data and letting you think about how close to the cutoff things should be limited. And Firefox is frozen again. I don't know if it's Zoom, because my computer likes to do this when I have Zoom open.
But so this shifts again or how you're trying to convince people, right? From, hey, I have the greatest method to, I think I chose the right bandwidth. I think I chose the right kernel. And you can still see this even if I change it, but it's smaller, but you really should believe my main specification. Like,
Yeah. Yeah, I mean, I think I always tend to err on the side of like, well, if you're not sure which to choose, run both and report both.
mhm.
Um, and then, just explain why you think one is better than the other. Or if they don't show different things at all, then you're just like, excellent. This is robust to different methodologies. Okay, so Firefox is frozen. I was going to suggest that maybe we could fit in placebo tests, but I don't know if that's gonna happen now.
I think that's fine. It's we still have a decent amount to go over, but I think we'll definitely be able to get through the rest of the chapter next week,
Oh yeah,
right?
we're more than halfway through the
Right.
chapter, so I think next week we'll have no problems.
Yeah. I'm wondering. Okay, yeah, I do. I think just backing up. Yeah, let's stop it here. Let me put it in the chat.
Perfect.